Labą dieną.
Sveiki.
Ar girdite mane?
Girdim.
Leisite pasidalinti ekraną?
Pirmiausia, jis pristatysi ir tuomet jau leisi viską. Good morning, Cyseni 2022 participants and listeners. It's our third day. My name is Cyseni. I am PhD student at Lithuanian Energy Institute and a chairman of this session. And I would like to introduce you to one more presenter, Professor Gintaras Valušis. He is a director at the Center for Physical Sciences and Technology, head of the Optoelectronics Department at FDMC, and professor in Institute of Photonics and Nanotechnology of Physics faculty at the Vilnius University. His scientific interests include terahertz physics and spectroscopy, optoelectronics, and physics of semiconductor devices. And today he will talk about semiconductor chips and the employment for color photos in invisible light. I want to remind you that during and just after presentation, you can write your questions in the YouTube live chat. Professor Gintaras Valušis, screen is yours.
Thank you. So good morning for everyone. So it's my pleasure to share my knowledge and insights on semiconductor chips and the employment for color photos in invisible light. So, in fact, I've decided to choose this topic because of a relatively hot attention to semiconductors recently, and I suppose it would be useful to introduce semiconductor itself and the general view of semiconductor chip situation over the world and even in our daily life, and finally, I will try to say how chips can be employed totally different manners that we are using in our everyday life, purely for security aims or recording a specific kind of electromagnetic radiation. So my contents of the talk will be semiconductor intros and semiconductor chips in general. Then I will talk about terahertz as a very high frequencies which can be recorded using semiconductor chips. It means that terahertz are quite higher frequencies and more than 100 times higher than usually chips are used. And finally, I will talk about colors photos in terahertz light. So so-called multispectral imaging, which is very useful for material inspection and also has a big prospects in security systems development. So initially, I will talk about semiconductors. So, you know, semiconductor is something in between two well-known state of solid state matters. Metals are conducting stuff, which is usually seen as a conductor. It means the best one is a silver or gold, and also insulator like a rubber or wood. And semiconductors, something in between. So, according to Encyclopedia Britannica, is some kind of crystalline solids, which conductivity strongly depends on temperature, and varying the temperature you can change electrical properties of such devices. So in fact, this properties allows to implement it into electronics, in particular for integrated circuits. But integrated circuits are one of the main important components in our everyday life. All smart devices contains a lot of stuff with integrated circuits, starting from our TV operators and ending by mobile phones or computers. So in fact, semiconductors is very important. And what is interesting here is that semiconductors can be, the conductivity can be changed, varying the introduction of additional elements. Like, so it's called doping. Semiconductors can be of n-type. When we have a free electron, it means semiconductors is a fourth group elements. If we introduce element of fifth group, we have additional electron which can have n-negative, so-called n-type doping, or we can go to another one, which is p-type doping, when we introduce a material from the set group. So in fact, we can have p-type or n-type doping, and it means that we can make p-n junction or two p-n junctions. It means either diode or transistor, and that it is the main components for the electronic devices. So semiconductor is extremely nice platform to make our world digital and to our world very smart. So in fact, transistor has a long history, and the main idea came from old times when William Shockley and Bell Labs in 1945 suggested to use a transistor as a bipolar transistor having two junctions. At the moment, it was not clear which kind of that can be done, and later, and so John Bartlett introduced a surface state. So in fact, people began to consider that if we have like germanium, at the moment it was the most popular semiconductor material, can be used to produce something like a device similar to transistor, which main aim was to amplify the electromagnetic radiation. So in fact, theoretically, it was predicted. However, real life says that in fact it's much more complicated matters. And the main issue that was understood later a little bit, that in fact semiconductor is not the same in the surface and the same in the bulk. It means surface states are present all the time, and surface states introduce surface field, which disturbs conventional transport in semiconductors. So, but in fact, people decided that in fact it can be done, and probably idea is just to make the device a little bit big, but to show the principle that such kind of device containing of two junctions can be applied for amplification of high frequencies. So what people did in 1947, important date, and at the moment, three important persons, William Shockley, John Bartlett, and Walter Brattain, and Bell Labs, close to the Christmas time, showed that point contact transistor can work as an amplifier. So on the left, you see how it looks like. It is a photo taken from the Bell Labs museum. Its device is relatively big, it contains spring, it contains a triangle shape device, and the collector with the spring, and it attached to the base, which was assumed to be germanium. And if we look from the side, you will see that in fact there is it's a germanium, so-called N-type. Here is semiconductor. We have a plastic triangle covered with aluminum foil. In fact, what we have is metal, gold. Then we have N-type, which is germanium, so-called base, and finally we have another metal which have a contact. So the first device was extremely big. I mean, in a centimeter scale. And it was so important that in fact it was big through in electronics. And in 1956, a Nobel Prize was awarded jointly to William Shockley, John Bartlett, and Walter Brattain for their researches on semiconductor and their discovery of the transistor effect. So lately it was understood that this is a new beginning of all the world. I mean, semiconductors began to play a crucial role, play a crucial role, and can be implemented in many things. So in what was happened, firstly, that the size which was used in the first transistor was extremely big. I mean, it's centimeters. So centimeters, it's not the case to go from the one side. From another one, it's just all this construction, if you see on the left, it's absolutely bulky. It is spring, mechanical, it's not stable. Collectors also spring, and also everything was made as attachments. It means there is no clearly contacting and reliable system. So the idea was needed to go further. And what has happened? People began to go to further. But what is important that this year we are close to the Christmas time, 23rd of December, we will celebrate 75 years of transistor. It means it's emeritus age, but transistor is still so important, and it seems to be that even more important that in the times of discovery. So in fact, what is also going further, it also needs to be underlined that field effect transistor, which is essential for our mobile phones, was invented even earlier. If you look at this historical patent written by Lilienfeld, it was 1930. It was happened 70 years ago, before originally bipolar transistor was invented. Lilienfeld just patented the idea that if you have a three-terminal device containing from source, drain, and gate, and if the gate voltage can be tuned, it means it can change the concentration in the channel, saying that in fact this principle can be applied for material which has two contacts but channel between them, and the principle itself can be used for electronics. When the gate is closed, there is no current. It means I have a jump of voltage. Once I open the gate, the current begins to flow. Voltage jumps down. I have a current. It means I can make a digitalization of the signal using such kind of device. Note, one submitted in 1926. There was no understanding about semiconductors at the moment, but lately, when semiconductor technology developed so well, this idea by Lilienfeld was successfully employed in so-called CMOS technology, which looks like this one. I mean, silicon devices with a metallic gate separated by silicon dioxide layer, and it's very similar to real device which has appeared several decades ago. And so one of the first principles shown in scientific literature, it was 1963 when nanowatt logic using field effect transistors using metal oxide semiconductor was published, and it was a first step for CMOS, so-called complementary metal oxide semiconductor technology circuits development. So we see its idea was so earlier, and at the moment there was no any clear vision how we can do these transistors, but principle itself was amazing, and it was implemented over several years, only several decades ago. So what is very important is silicon integrated circuits. So I mean, for first device, the first transistor was made from germanium, but it later was understood that the thermal properties of germanium are not so promising. When you have a current inside, it heats and it changes conductivity, and germanium is very sensitive. It means working regime is not so stable as we would like. So in 1954, the first silicon transistor was invented. It was done by Morris Tannenbaum in Bell Labs. And at the same time, it was commercialized and also big competition. Texas Instruments was one of the leading companies at the moment, and the same year, the first commercially available silicon transistor. So it looks like this one. So in fact, it's a relatively big, but it was a really commercially available device. So 4 years later, Jack Kilby from the same Texas Instrument made the first integrated circuit. So what you see here is just a picture of the circuit, and it contains only two transistors, but they were connected with the wires and saying, okay, I can make a system of transistors which can work and can extend it to this other numbers of transistors, and I can make a huge amount of transistors. However, main issue was to decrease the volume. So Jack Kilby showed how big it was still on a hand and at no still in centimeter scale, and no nothing was less than in millimeters. And the main ideas came from the labs, what you see in the picture. So here it was another one, another important person behind this. It was Rob Norton Noyce, also together with is parallelly to the Texas Instrument. He also invented first silicon chip. It was done in a company called Fairchild Semiconductors, and he was a founder of Fairchild, and later he was a founder of co-founder of Intel. So he very smart guy. He was very famous physicist from the one hand. From the other hand, he has a good feeling of high-tech business, and he initiated Intel as a leading high-tech company in United States. So in fact, it was this decade in 1956 and 1959, it was two important years in evolution of integrated circuits. And so what is important to underline, so transistor has a gate. Usually you see here the same, and how it looks like. It means a processor, which is shown in the photo of Intel. Here is attached in the electronic circuit, and it can be part of computer or any type of mobile phone. But so important stuff here is the length of gate. I called it L. It means how long is a gate of the transistor. It means how fast electron can travel from some source to drain. And there's a time to crossing it defines a limit frequency of the operation. So that's the most important stuff, and it mainly defines the scale, frequency band of all the devices. So what we have at the moment in our daily life, it's FinTech technology, which is usually used for our mobile phones. It contains a lot of transistors in our mobile phones or computers. So FinTech, it means I have a gate which covers, you see in the photo, which covers as a drain source structure. So to illustrate in numbers, I mean, which kind of a scale we have and how many of transistors we can have in our system is like as a scale. So you see that Galaxy, for instance, is old stuff. Galaxy, something like S3 or Galaxy A4 had a relatively long gates. It amounts to 40 nanometers and 28 nanometers. So iPhone, you see here, it's on the same time scale. You have about 45 and 28 nanometers. So big companies competing in the mobile phone markets. So later generations, idea was to decrease the length. It goes down from 20 nanometers to even lower. And for instance, iPhone X, it amounts about 10 nanometers, iPhone 11, 7 nanometers, and producer of microchips for mobile phones is TSMC, company from Taiwan. So it's Apple. If you go to Samsung, the story is different. Samsung has original fabs and producing original processors, and Galaxies are also in the same area, about 10 nanometers. And for instance, if we look at the latest, iPhone 12 and also 13 has a 5 nanometers, but recently appeared in February, a Samsung Galaxy appeared with the name of Ultra 5G. The shortest channel is 4 nanometers. So in fact, we have commercially available system, which is extremely modern. and the scale is the lowest at the moment. So what is, if we look at from another point of view, we have something like frequencies, and if you have let's say comparison of iPhone and Galaxy, what we have is operation frequencies. You see here is the gigahertz range. The 1 gigahertz is 1,000 million of hertz. It means it's relatively higher frequencies, and usually this is conventional operation frequency of mobile phones, of mobile phone processors, while our scale of operation of in communications is slightly lower, reaching 1.9 gigahertz. So it's a scale. Gigahertz range is operation scale for mobile phones. So if we go further, if you go further, this is 4 nanometers, is a world record at the moment, what we can have in our hands. So to illustrate and to get broader insight, we can go to comparison. So how we can define what does nanometers means and what it's important for our everyday life. So in fact, this nanometric scale does not mean that our transistor is in exactly 5 nanometers length. It means that we are using technology of such a range. It means process technology or technology node defines which kind of lithography we should use. It means 5 nanometers means that we are using 5 nanometers technology node, but it means that our device is slightly bigger. So in fact, usually it's now it's understood as a node, and usually, as I already mentioned in nanometers. So the scale, what you see here is evolution, what we have at the moment. It's taken from one of the companies. Evolution was initial state was 250 nanometers, and then begins go down, and go down. So you see that every 2 years the node changes, and sometimes changes slowly, more slower speed, and sometimes it goes rapidly. But in fact, we're keeping all in mind that we're speaking about nanometers. So what is important? I mean, TCMC defines as another picture, and I would like to make some distinguish 2 different processes. So complementary metal oxide semiconductor technology being the most important and the main technology for semiconductor production can be divided into the 2 parts. I mean, drawing the line around 40 nanometers, saying that nanometers is something like a threshold indicating where application areas can be used. So application in cars usually reaches about 40 nanometers or even higher. It means 65 or 90 nanometers. So if we go down and go to this area, application can be totally different. So in fact, there is predictions. Big companies making prediction how evolution can go further, and you see here is prediction. Usually the scale is around 100, even higher, but in fact it's quite enough for auto car industry. So there is no need to go to several nanometers if we intend to use chips for cars or other devices. If we need to use them in mobile phones or computers, you need to go very short scale, because it allows you to increase the speed and also to decrease strongly as a power consumption. So that's the main consideration. So in fact, 28 nanometers is important also numbers. It means that below, simply the processes can be, there is no licenses at the moment below the scale. It means factories, fabs keep this technology for yourself, or companies uses this but do not distribute the technology for others. So what is important to note also is that 4 nanometers appeared in 2022. It means 2 years was needed to reduce the process node to 1 nanometer. It means the next step could be 2 or 3 nanometers, but still they're far away from implementation in in commercial applications. So, but Samsung now it seems to be the leading company, and while we do not know what's going in TSMC, but probably also they also have in the labs, probably not implemented in commercial devices at the moment. So some numbers, I mean, what it means nanometers. I mean, human ear is about 50 microns. So in fact, CMOS transistor is about 10,000 times smaller. So iPhone 12 contains nearly 12 billion transistors using 5 nanometers technology. iPhone 13 contains more than 15 billion transistors with the same technology. So, and frequency operation usually, as I already indicated, was slightly exceeds 3 gigahertz. So Wi-Fi we are using every day in our houses or flats and labs. So there is usually can be of with two ranges. I mean 2.4 gigahertz containing 14 channels and 5 gigahertz containing 25 channels. So in fact, frequencies are pretty low in comparison to big further. And Bluetooth technology, which is used also for communication between devices, it usually works at 2.45 gigahertz. So to indicate how many chips we have and why there's big delays now in ordering cars and what's the big delays in car productions, it's a huge amount of chips used at the moment. So electric auto cars has about 22,000 chips. Normal conventional car, I'm bearing in mind diesel or normal car, it's about 1,000 chips. It means mainly dominating by two technologies, 65 or sometimes 40 nanometers technology. So it means that even our conventional car was normal engine still very smart, and still the services, all this control, engine control, all the surrounding control, and all control of any technological processes occurring in the car still needs a lot of chips, and this chips amount is 1,000. That's big need now for factories. That's big man for production, and that is why pandemic situation, because of huge demand of computers and mobile phones and laptops, just strongly decreased the production of chips for auto cars, and we have a delay in the market at the moment. So that are numbers for illustration. So if we look at the whole ecosystem at the moment, what is usually not visible, but if we look at this intellectual property rights, and you see how much we need a software to produce it. And if we look from one time how looks as companies using software or developing software for production, so you see that situation is very interesting. Chips are produced in a fabs, different companies using either original or software developed by other companies. And you see there is, if you go with this triangle, you see that on the top we have only several of them which have both and fabs, development, design, development, and also software. So in fact, it's original ideas, software licenses, production, and new products appearing in different kind of devices, starting from mobile phones, cars, planes, rockets, and something like that. So in fact, ecosystem is relatively unique. It means that there is contains intellectual property rights issue, which is not easy, and licensing is quite expensive. It depends only, is only academic or is also industrial. So that's the story. So ecosystem is strongly mixed with the intellectual property right of the companies. So if we look at the foundry, so at what is leading companies at the moment, there are only two of them, Samsung and TMC, producing most advanced devices at the moment in semiconductor chips area. So if we go further now, I mean, as I already mentioned, our operation speed, our frequency scale reaches several gigahertz, 3 gigahertz or slightly higher. Communication system is below 3 gigahertz, 2.5 and slightly higher, but in fact it is gigahertz. So idea is it possible to use them to much higher frequencies? Because much higher frequencies allows us to transfer much more information, which much more to establish much more channels and to provide totally new generation of communication systems. So we'll go to terahertz. Terahertz is 1,000 times higher frequency scale that is gigahertz. So in fact, importance is that in fact there is scale which is in the electromagnetic wave scale. It is between photonics and electronics. For physics, this means very simple things that in fact electron velocity usually goes about 10 to 7 centimeters per second. It's not cannot go faster. Simply. But when you're reaching such a kind of frequencies, conventional transport stops. From other side, when we have important stuff, is that our operation in real life is room temperature. It means 300 K, and in energy scale, it means 25 MeV. It's relatively big numbers. So if we try to go to work with this field from photonic side, it's splitting is too small. I mean, terahertz quantum is too small. Splitting between states is something like 1 terahertz. It's only 4.1 MeV. It's, you see, room temperature is much higher than this 1 terahertz. It means we cannot make normal population inversion. So this distance between small, and it means electron will jump between the levels, and to produce a laser is a big issue. So in fact, we need a very strong and unconventional approach to solve this problem, and to construct the device needs absolutely different approaches that used used from a conventional transport or the photonic. It will be something like mixture or something like intermediate solution, which allows to design an operational device. So there are two ways to produce them: is optoelectronic terahertz and solid state terahertz. Will go first, but what is important, that terahertz is only implementations. There's a lot of terahertz in the universe, and usually radio astronomy also uses this range to understand the origin of universe. So Peter Siegel 2 decades ago published interesting article, terahertz technology, indicating how many terahertz we have in the universe. You see how looks the spectra. It means a lot of absorption in atmospheric in our atmospheres, but also terahertz spectra is rich because of various sources in the universe. It means if we are able to measure, we can understand origin of the universe. So in fact, if we look, nearly 98% of photons from since the Big Bang falls in this range. It means radio astronomy is important area to understand origin of the universe. And so because of a lot of gases and spectral signatures containing in this area. So in fact, what is important, measurement technology in astronomy is so big, it needs 12 meters long diameter scale to have a radars or telescopes to collect the light, and the coding system contains absolutely unconventional approach using liquid helium to low temperatures, so huge system. But what we need to do from large scale, from universe scale, to go to on-chip scale. So in implementation of terahertz or high frequencies somehow should fit to the mobile phone size or on-chip scale. So our task is to look how we can go with this one. So terahertz is so important in securities. You know what you see here is industrial security. If we put something inside the envelope, we can see it inside, and also without any opening of them. So medical diagnostics, bioimaging, communications can be also the way to go, and also color spectroscopy, what will also show, will command this colors photographs and target frequencies, and also explosives detections or security cameras. If you have something behind your in your pocket, it can be easily recorded because targets easily propagate through windows or post packages. So, one of the examples how we can go is application of Tokyo Post Office. You know, we have inspection people in Japan like a normal posts, normal envelopes, and you need to check whether it's okay or whether it is something dangerous inside. So, in fact, there is a system allowing to check them, and mean suspicious mails can be separated by separate channel, and it can be applied in using target spectroscopy to understand what is inside. So in fact, if we go, usually its multiplier system and its generation can be done in an electronic way. It reaches about 2 terahertz, and this area, it's not all areas needed for securities, and security is restricted mainly below 6 to 7 to 100 terahertz. So application security, it looks like this. Device you see here is it's just taking a photo in our lab. It's a relatively bulky device as well. It's not chip solution, but it works pretty well. And what is important here is a photo of this Tokyo Post. You see here is terahertz units. There's a lot of them. It's X-ray unit when you scan post package. Then it's visible camera to look how it looks like, and then it's terahertz camera, and terahertz camera records a scattered light. You know, if I put, for instance, coffee inside this envelope, I can see how it looks like. You see here it depends on the powder size, and usually this picture can be obtained using scattered light. So we see here is 2 frequencies, 600 and 300 gigahertz. It means 100 times higher than mobile phone operates, and as the light is scattered and signal to noise ratio is very different. It means that this area much better because of better signal to noise ratio. That is why security systems requires about 5 or 600 gigahertz applications and recording systems. That's the reason. So in fact, it's security application which is important for us. So in fact, the requirements, room temperature, usually scale below 2 terahertz is quite enough. Quite sensitive detectors. Emission should be also the same, powerful, tunable, preferably tunable, and also 300K in room temperature operation. And spatial mode should be very good. And also compact, convenient optics also should be present here. Not like a case in our photo. You see here it's relatively bulky, and it means you need a scientific environment to work with it. So usually terahertz are generated using such a femtosecond laser system, and it is a relatively complicated way. What it runs, it records a transient, and Fourier transform of the transients is nothing else like terahertz. So in fact, what we have, electron just excited were accelerated by the field, and electron moving with acceleration emits broadband terahertz radiation. That's the principle. Usually what we're using in our labs it's system like this one. You see it's also bulky, but terahertz source usually electronic. We're using something like 100 gigahertz, and was multiplied by a factor of 2 or 3 or 6 to reach this area, and it allows to have this terahertz radiation, which is CW based, not pulse mode. So what we did, I mean, how we can use this, our original ideas, we're using bow tie diodes. You know, bow tie is something like using enclosing. You know, you can use as a part of your clothing. But you see, it's not normal. It's not closed. Not textile material. It's semiconductor material. It is broken symmetry. Part is metallized, part is semiconductor, and if we apply such a system in something like that, so device looks like this one, it focused radiation. What we have is voltage over the device. It means it can be used to record the radiation, and if the device is placed on silicon lens, it can really worked nicely and collects the light from a relatively large area. Diameter is 1 centimeter. The diameter of the lens is 1 centimeter. So how it looks like? We produced arrays using such kind of device, and material is used as indium gallium arsenide is semiconductor material, approaches optical lithography and wet etching, and you see our chip is only 8 diodes, not billions of transistors at the moment. So, but if we're applying this one, our detection system is coherent. We're using heterodioning, which was used in astronomy, which allows us to decrease the noise flow. So it's tricky thing, allowing us to have very good detection system. And it means from the normal detection, we using coherent detection, we can reach 4 orders of magnitude higher signal to noise ratio. And our imaging looks like this. What we did, we placed it medicine in an envelope and tried to record the images. You see a direct image, you see heterodyne image and a phase image. You can see what is inside the envelope. And also we placed a leaf from the tree and recorded also a normal scheme, direct scheme, heterodyning scheme, and phase scheme. You see its weakly absorbing material is nicely visible. And so what is important in the reflection geometry, we used Lita's coin, and here you see coat of arms sign. And what we placed it is, you see in the covers applied physics letters, just because of this coin has a scattering efficient light scatterer. It means instead of beautiful picture, we have a scattered light based picture, which makes some piece of modern art, which were found for editors very attractive, and that is why it was placed on the cover. So, but here is diode scheme. It's mainly diode scheme, and our idea is probably we can go to transistor scheme. So transistor scheme is something like that. We need a channel, and channel is something like that. So idea is that as fast transistor goes here, it works pretty well. So, but frequencies usually is several gigahertz, as already indicated in mobile phone operations. But we can reach something limit like 50 gigahertz or even 100 gigahertz, but never terahertz. So, idea was to employ acoustic or plasma wave in that. So, when I'm speaking to you now, my voice just goes through vibrates the air, and acoustic wave reaches microphone and converts my speech to the electrical signal. So if ever would be two-dimensional gas, equivalent of acoustic wave in two-dimensional gas will be plasma wave. So if I speak in two-dimensional electron gas, my acoustic wave will be plasma wave reaching microphone and to converting the signal in the same way. So it's faster. Sound is faster than normal transport. So plasma wave is more than order of magnitude faster than conventional transport. So in fact, I can go to terahertz range and to employ this. So in fact, the famous paper written by Mikhail Diakonov and Michael Schur saying that in fact, if I have something like that, my channel between source and drain can be assumed as a special space for propagating of plasma wave. Plasma waves which are faster than conventional transport. So what is important? It can be tunable by gate voltage. It can operate in both mode, emission and detection, no temperature limitation. And since it's transistors, it can be easily integrate in a circuit. So nanometric transistor was demonstrated experimentally, and you see here is very nice spikes at 600 giga, which is far beyond the cutoff frequency. First demonstration by Wojtek Raab group in 2002 encouraged huge amount of work and a lot of nice scientific results. And the frequency was mainly defined by the length of the channel and the mass of the electron gas. So what we did in our labs, we demonstrated that we indeed such kind of transistors, where if you're changing the material to another one with a lower mass and a little bit shorter channels can reach easily 3.1 terahertz. So it's important discovery published more than a decade ago, but it stimulated huge amount of research for both research and applications. So gallium nitride was found also good as a plasmonic emitter, and if you look here, this gallium nitride is much better in the point of view reliability transistor material in comparison to silicon, and it allows to reach 2.1 terahertz in operation. So what we did, we decided just to go with transistors, and in fact, a group by Wojtek Mok and again, more than a decade ago, demonstrated that if the transistor can be integrated with a broadband antenna, it can record images, and even needles placed in a chocolate can be observed. So this work just showed that these numbers, which are here, I mean, with broadband antenna, allows to reach very low so-called noise equivalent power, which is extremely sensitive even in room temperature. So what our group did together with Frankfurt group, we constructed the chip, which is totally different that used in mobile phones. Our chip consists of several places, which were composed for different kind of colors, and every color has a special antenna patch and used for different frequencies, starting from 200 gigahertz up to several terahertz. What we did, we recorded the operation of this device. I made a photo of something like of simulator explosive simulators. So we see this picture, which you see different shadows at different frequencies. It means even if I do not measure spectrum, I still can resolve the content of the materials which is inside the pellets. So it's used, we use 60 nanometers technology, and it allows to reach 4.3 terahertz. And we used plasmonic mixing instead of conventional carrier transport. That's the way to go to higher frequencies. And here's another colored photos recording by another stuff. You see how the samples look like. It's a photo. The simulants contains sucrose, contains tartaric acid, and the mixture of both was in the range of 5%, and was easily recorded. It's another recording by using bolometers and something like that. Our colleagues initially demonstrated also images using commercially available gallium arsenide FETs, and here is metallic cross placed in the envelope, and the key placed also in the envelope in the reflection geometry. And also very recent results, images and 1.40, 1.70 gigahertz using gallium arsenide nanometric FETs. It's courtesy from Frankfurt groups. It's also, you can check the food, whether it contains something metallic stuff or not, easily without any additional efforts, without any specific kind of research, just using high frequency radiation of 170 gigahertz. So that's the way to go. So transistors, is it possible to make transistors which emits them? So in fact, many years ago, it was considerations that multipliers can be done in very compact way. And with the channel length, which you see here is still, it was supposed that 65 nanometers should be the case to go. It was old work. What was done recently, Lithuanian group together with Polish people made extremely nice work that all emitter system can operate at 205 gigahertz in silicon. It means 100 times higher frequencies that mobile phone operates at the moment. Designs you see looks like this one. There is no billions of transistors. There are only several of them, but the principle is to show that it works nicely and can still emit the power reaching nearly 200 of microwatts. Power is still low for commercial application, but principle in itself, it works nicely. So in fact, what you need to do this, you need need a total chain of technological solutions, starting from growth up to device production and direct implementation. And it means we need to have facilities to produce chips, to test them, or to have processing technology needed for semiconductor device precise production. So finally, we'll go to high-tech numbers. Is it possible to do in Lithuania? So if you look at the most dominant parts in photonics and lasers, we have a huge amount increase in high-tech technology. Lasers, it's conventional increase about 10%, and added value created for each person per year exceeds 160 kilo euros, while in electronics we have much better increase, slightly lower added value created by one person, but still big amount. So foundries, what's the price, for instance, for the foundries? If you intend to build a foundry of 65 nanometers, it costs about 1.2 billion euros. If you go to 40 nanometers, it goes to up to 3.5 billion. And the latest Samsung foundry and development in Austin, in Texas, in America, nobody knows exactly which kind of that, about probably 3 nanometers, it costs about 17 billion euros. So finally, optimistic notes, it's a very important events in political level. European Chips Act encouraged to go in this way to have a production in Europe for semiconductor chips. Companies and scientists are encouraged to participate and to run startups and to reach at least 20% of world production. At the moment, we have only 10 in Europe. So ambitious goal at the moment is below 7 nanometers and 22 nanometers. Idea is to go further and to reach at least 5 nanometers. So what application is 5G and 5G components for terabit communications? Idea is to go to 2 nanometers in FinFET production and 2 nanometers in SOI, so silicon on insulator production for quantum computing and something like that, to produce pilot lines using IPCEI projects, recovery and resilience funds, and also to introduce artificial intelligence in this kind of devices. So it's good point to go, and Europe and CHIPS Act allows to do this, and we hope that our scientists also will go to this way. So that is my final words of my talk. Thank you very much for your attention. Thank you.
Thank you, Professor, for this outstanding presentation. I have no doubt that everyone was astonished by your presentation. I see that no questions in YouTube present, but I have a question.
Yeah.
Nowadays, world face the problem of semiconductor shortage. Does this affect your research somehow? Done work, or you make it by yourself so you are not affected?
Well, you know, I mean, what is not mentioned probably, we can try to join photonics approach together with electronic, it's so-called 3D hybrid integration, which needs a lot of research. So in fact, what is important, CMOS technology is not available in Lithuania. You can make a design and order somewhere. What is important, photonics tools are available at VMTMC and Vilnius University and partly in Kaunas University. So that's the way to go. I mean, I see the broad area for participation and probably good opportunities to participate in European projects or probably world-scale projects.
Okay, thank you for your answer.
Thank you.
I see no more questions. So, Professor, we are grateful for the time and effort you took to share your thoughts and experience with us. Again, thank you. Hope to see you again somewhere soon.
Thank you. Thank you. See you later.
Thank you. And before closing this session, I would like to remind you that at 11 a.m. Central European Time, we have a physical science sector poster session in Gather Town. We will meet there. Have a good day.